In 190 A and B, our group will focus on making a microneedle sensor for detecting serotonin level in human bodies. Biosensors are used for detecting and monitoring many diseases nowadays. For example, CGM can detect glucose in your blood and thus help monitoring diabetes. The problem is that traditional biosensors you often use invasive mechanism. Oftentimes, they poke a 1 centimeter long needle into user's skin, and it can sit there for 1 to 2 weeks based on the sensor's type. And in this process, it can cause pain and discomfort for the users. And our group thinks there's a need to improve the current sensors in the market. When we look into the search volume of these sensors, people are asking for sensors without needles, which further proves the need for a non-invasive, painless procedure. And surprisingly, they are also asking for sensors to help continuously monitoring neurological diseases. In order to achieve that, we think we can detect diseases use biomarkers in interstitial fluid. For example, serotonin is a good thing to look at because it's an important parameter to monitor depression. And the defining question is how might we formulate or commercialize electrochemical non-invasive biosensors that use interstitial fluid for real-time detection of serotonin? And our answer would be using microneedles.
Moving on to the ideate stage, in academia, we noticed that there was a lot of research in electrochemical glucose sensors. So, kind of following that direction and combined with our interest in neurological conditions such as Alzheimer's and brain tumors, we decided to produce a serotonin biosensor. Conventional serotonin biosensors, such as immunoassays, colorimetric sensors, are typically invasive, cannot acquire results continuously, and are in vitro. We decided to use microneedles as they are non-invasive and can access interstitial fluid 500 microns below the skin. Microneedles are typically 500 to 2,000 microns in length. We chose electrochemical microneedles as they offer high sensitivity and selectivity of small concentrations of serotonin and ISF. Electrochemical microneedles can also be easily integrated into non-invasive and real-time monitoring, as well as in vivo testing. So our final project is now non-invasive electrochemical microneedles for detection of serotonin.
For the prototype section, how it works is that the needles will be fabricated from molecularly imprinted polymers, and these polymers will work to bind with serotonin in a lock and key mechanism to allow for detection. What we're going to start with in testing is in vitro simulation in agarose gel. For a control, there will be a gel created with no serotonin. Then, different levels of serotonin will be tested on different gels, and the differences in the data recorded will be used to test the sensitivity of the device. So, for the summary of materials, the resins for 3D printing, the graphite and mineral oil will be used for carbon ink. We'll need AgNO3, GO, D-glucose, and ETOH for the Ag-RGO synthesis. Then we will need chitosan for polymer binding agent, the silver epoxy ink, and copper silver wires for electrofabrication, ferricyanide solution for electrode activation, PBS, KCl, and artificial ISF for the electrochemical testing, and finally, agarose, PBS, and 5-HT solution for skin simulation for the in vitro testing. For gear, we will be needing to use a 3D printer, resin, post-processing station, a sonicator, a UV curing chamber, and micropipettes. By week 5, we would like to have the first prototype started on in vitro testing. For who is doing what, Milana and Nora will be doing in vivo and in vitro testing, and Chipra and Yi Yang will focus on fabrication.
So the testing procedures that will be done in 120B include cyclic voltammetry to measure the electrochemical behavior of serotonin, square wave voltammetry since it offers sharper peaks and is able to detect lower concentrations, and we'll also be using in vitro skin simulation using agarose gel, and also hopefully in vivo testing using mouse models.